Thanks, Andy. All right, well, that was pretty cool, having two of the industry's key thought leaders over many, many years talking about how to make photonics real and the investments that Intel has made in research development and bringing this cool new technology to market. With that, I also have the honor not only to share the stage with people like Justin Ratner and Andy Bechtolsheim, but I also have the opportunity to introduce my colleague at Facebook, Jay Parikh. Jay is going to come and talk to us about some really cool challenges that we're seeing at Facebook in the area of the rapidly exploding data storage requirements that we have. And if we get this all right, this may be some future contribution that Facebook makes to this community. So with that, I'd like to welcome my colleague Jay Parikh up on stage.
Cool. All right. So, put this over here. You know, it's great to be here. It's our 4th summit, and it's only been less than 2 years, so it's really impressive. You know, I was walking around last night late with Frank over here, and the thing that really struck me as I walked around there was there's so much toys to play with now, right? A year ago, 2 years ago, everything else was like PowerPoints, poster boards, brochures, photos. Well, we actually have real stuff that people are building and people are using today. So that was like the most kind of impressive thing that I saw last night. And I wanted to thank everybody for all of the participation and the contributions they've made over the last 18 months or so. There's a lot more to do, and it should be an exciting couple of years here. Let's see, there we go. So, you know, when we conceived of the idea 18 months ago or so, 2 years ago, for OCP, I always thought of it as an essential response to the challenges of big data. Now, you fast forward kind of 2 years later to today, the scale of these challenges are basically far greater than we ever imagined. So basically the OCP efforts that we started and that we've been working on could not have been better timed in my mind. I wanted to start off, though. Everybody's familiar with sort of the concept of the term big data. I wanted to start off being a little meta, so let's look at some data about big data. All right, so back in 2010, the estimate was that there was about 800 exabytes of data that had been created and replicated in the world. The crazy thing about this stat is that 90% of this data had only been created in the 2 years prior to 2010. Now you fast forward to basically 2012, the end of last year, just a few weeks ago, it was estimated that there was 2.8 zettabytes of data created. Basically 2 zettabytes of data had been created just in 2 years, so you can see this tremendous growth. Now as they've done predictions, the IDC sent out folks to analyze this, and they came up with a prediction that said, hey, in 2020, there's going to be 40 zettabytes of data in the world. Now, to put this in perspective, they sent out a little analyst to go count all of the grains of sand on the beaches of the Earth. He came up with 700 quintillion, 500 quadrillion grains of sand on all the beaches of the planet, or on the planet. So, you know, this in perspective is that the 40 zettabytes is going to be 57 times the number of grains of sands on the Earth. Now, I personally really didn't know how to put this in perspective, so I thought to myself, I was like, well, what does this really mean, right? So in 2020, there's another stat, which is that every man, woman, and child on the planet will have basically 5.3 terabytes of data just for themselves. So I was like, okay, well, what the hell does this mean, right? And I was like, okay, so if I take a picture, or if I just say, hey, this is all photos, this is going to be over 2 million photos per person. And I was like, okay, so what the hell does this mean? And then I did some math, and it basically came up with that if you were to take a picture every 15 minutes of your life from the moment you were born till the moment you died, that's how many photos you would actually accumulate. Every 15 minutes for your entire lifespan, that's the type of volume of data that we're accumulating. So this is kind of a, to me, it's just unprecedented growth. And the funny thing about all of these estimates, if you look back over the years, they've always been wrong. They've always been on the low side, right? So every time, every year, these estimates, like the actuals way far exceed the estimates that we come up with here. Okay, so, billions of people and billions more devices are coming online. The folks that are actually already online are leading ever more connected lives. They're doing more stuff online. They're engaging in more applications. They're doing stuff. So the data growth here is exponential. There's no sign of this slowing down anytime soon, right? Same time, all of you guys are familiar with this, is that businesses are focusing more on using big data to get real-time insight and or value from their data. So everything's getting more focused on, hey, what can we do with this data now? How can we change sales? How can we change the customer experience? How can we change the product? So we're really focused on just looking at the most recent data. The funny thing that I always scratch my head at and say, so, well, cool, if like we only cared about the most recent data, then we can take the old data and just throw it away and we don't actually have any big data problems, right? But we all know that this is like impossible. There's legal reasons, there's security reasons, there's financial reasons. Customers won't let you. As I talk to my friends in the Valley and other industries, they say, well, we don't really know what we're going to do with the data, but we're going to keep it for, quote unquote, future option value, right? So this is one of those things where you have to solve this problem. There's a lot of opportunity here, but there's definitely a lot of challenges as we talk about this. So the question for me is, well, how do we keep up with this? So I want to talk about a Facebook service that has consistently been hard for us to keep up with, just given its growth. Facebook Photos. So hopefully everybody has seen or heard about this product or used it or uses it every day, but it's essentially become a mainstream way and a really important way for people around the world to share their memories, their experiences, their events with their friends and family. It's an amazing immersive experience. The growth that we've seen has been unprecedented, but in the last 3 years, we've seen really astonishing growth in the system. So today, we have roughly around 240 billion photos. Now, this is unique photos that our users have uploaded. Users are uploading more than 350 million new photos every day, and this is actually only increasing as more and more smartphones get out to people's hands around the world. We consume today over 7 petabytes of storage capacity every month, and this is just for photos. So this presents just an enormous growth and sort of scaling challenge, right? It's been really hard to keep up with. The thing that we kind of struggle with is, okay, so we have this really amazing immersive experience that's used so broadly, it's so integral as part of our product experience, but so what's the problem here, right? So the problem here is that we can't lose any of these photos. Our users expect us to keep these photos and these memories for years, decades, as they accumulate sort of their lifetime of memories and experiences with their friends and family. But what this actually means is that we have to keep lots of servers around. This costs lots of money to make sure that we have all of this data and these memories for our users. The other side of this is that we need to keep a really fast user experience. We can't just put all these photos on tape and say, hey, you want to look at that picture of Halloween 5 years ago? We'll go run over and grab the tape and put it on the drive and load it up and we'll send it to you in a week. That just doesn't work for our user experience. So the problem here, though, the opposite problem here is that we have to actually use a lot of power to keep this stuff powered and sort of online and active all of the time. So for us, it's like, okay, well, you look at this and you're like, wow, what are we going to do? So it turns out that as we looked into the actual usage in the product, and as you might expect, the access patterns of this data really dramatically vary given our product design. So I want to talk a little bit about this. So here's my timeline. Here's a photo of my daughter and myself. Don't worry, no dads were harmed in that photo shoot. So, when the photo is actually uploaded here, my friends are going to see it because I upload it. It's going to get posted in people's news feeds. It's going to get distributed out to all my friends. My friends get to comment on it. They're going to get to like it. They're going to get to share it potentially. They may tag themselves in photos, right? Or tag other friends in there. So there's a lot of interactions, and this is when a photo is hot. Over time, as basically other news events come up and that content kind of pushes down in news feed, you're going to see basically the interactions on that content taper off. And eventually, sometime later, there will be very few interactions, and it's just kind of a memory that will be sitting there. And if I go back and look at through my timeline or somebody else looks at my photo albums, they'll be able to see this photo. All right, so let's take a look at this in terms of more specific metrics around this. So here's a graph. The green line here is basically read traffic. So it's the read traffic that goes into our photo volume. And you can see here just by the shape of this curve and the x-axis here that most of the traffic that we experience is actually for photos that are new to the system. Kind of intuitive given what I told you about sort of newsfeed and timeline and the experience here. Now, The orange line here is basically a percentage of our photo volume by age. This is just kind of the growth and sort of the distribution of the age of the photos in the system. Now, if you line up these curves, the thing that is pretty cool here is that 82% of our traffic, the inbound traffic to request and sort of serve a photo, is actually only focused on 8% of the photo volume. So one of the aside points that I wanted to make here is that I think big data is and needs to be dissected like this. You have to understand the absolute value of your data and how it's growing, but you also have to understand the access patterns, how it's actually being used. I find in talking to colleagues in the industry that they do sort of a one-sided capacity plan. They look at their data and they say, okay, we're using this much, we're growing X amount every month, we'll just keep buying and sort of stacking things up. But they never take the time to actually look at the data and see how the business and the applications are using that data. So you end up with what I call dark matter, big data. There's a lot of data that you accumulate and you think you're using and you're not actually using it. So this graph is kind of crazy to me in another way, which is there are over 200 billion photos in our system that are infrequently viewed. But yet they've been and traditionally stored on the exact same servers that the hot photos that are popular and being interacted with are on as well. So this spells, hey, this is really, really inefficient here. So we basically came back and said, hey, there has to be a different way to do this. We have to be able to come up with a more efficient infrastructure for how to support the scale of this product over time, because this growth is not slowing down. As I said, more and more users. We support 1 billion users on the planet today, more smartphones. This stuff is scaling really, really rapidly, and it's going to continue that way. So we took kind of a full stack approach here. We basically said, hey, what if we could rethink everything? And usually in the Facebook motto, we end up rethinking everything, and then we decide to change everything. And then we change everything at the same time, just to make it a little bit harder for us. So we looked at basically the data center, the software, and the server, and we focused on trying to maximize the efficiency of each one of these stacks and then how the stack actually works together. But we had to preserve our product experience. I couldn't go back to Mark and say, hey, you know what, that photo of you from college, it's going to take 4 hours to load next time you try to look for it. So we need to make sure we kind of didn't make this impactful or viewable or visible to our users. So I want to give you a quick tour of sort of the first piece here. So we started at the data center. Now, a conventional data center, the design points here are basically maximize power, maximize compute per square foot, right? You build these data centers, you add lots of cooling, you add lots of electrical power redundancy to the systems as well. For us, it turns out that what we needed was a lot of space. We didn't need a lot of power. And then we looked at all the electrical redundancy systems and said, you know what? We don't really need all of that. We'll kind of push it off to the software. I'll talk about the software in a minute. So it turns out what we ended up really needing was the exact opposite of what one of our conventional data centers that we've built ends up looking like. So some of the specifics here are that there's essentially 1 exabyte per room, and each one of those kind of pieces off to the right is each room is sort of a module that is 1 exabyte in size. So you add up 3 rooms and you get 3 exabytes total in one building, and we're building many of these buildings. So it gives us a semi-modular approach to our capacity planning. Each building kind of stores roughly about 500 racks, would consume about 1.5 megawatts of power. The other thing we did is we looked at UPS's generators, all of that stuff. We threw it out. There's none of that there. There's power to the building, to the servers, and that's it. It's very simple. This is the way that we were able to cut out some of the cost in the system. So I want to move on to the software. The software is where the sophistication really, I think, is kind of moving to for us. It brings together all of the really interesting things we've done at the physical layer and makes it sort of work together as one complete system. Now, if you see from the slide here, we're designing for many different goals and many different constraints. We have this massive scale that I talked about that we have to support. We have to make sure that we have high durability, we have high throughput, and that we're making the storage systems efficient. We need to make sure that we optimize the numbers of copies of the data and where the data is stored at all times throughout the system. The other thing here that's also interesting is that the software has to account for the fact that we have very low power redundancy in the data center. We have network bandwidth limitations, and I'll talk about the storage stuff, but there's power management issues in the hardware. There's heterogeneous different types of devices that we store the physical bits on, and these devices may or may not have higher failure rates given the quantity and sort of the scale that we're going to be deploying them on. So we had to make sure that we're going to sort of deal with all these constraints in an effective way. Wrong button, sorry. Let me go the other way. So we have a concept here. At Facebook, we have many different storage systems. We have a system that we've talked about in the past, a system called Haystack. Haystack is the system where when I upload that photo, it's a hot photo. And that photo is stored on many, many different spindles. It's stored in Flash. It's cached in the CDN. And we optimize there for fast performance. That's the only thing we care about in Haystack, is make sure the user experience, the upload is fast, and the serving of that photo is fast, because we really want to maximize the interactions that I showed earlier. But over time, we have another system that we call warm storage. And what we try to do is kind of start to really look at the number of replicas of this data that we have and start to compress it. It's still online, and it's still next to the hot stuff, but it allows us to basically store it a little bit more efficiently. Now, I'm not going to be able to go into details on both of these systems, but the important point here is, and I'm going to talk about cold storage, but the important point here is that we have sort of an architecture that allows us to basically compose or mash up these different storage systems, the hot system, the warm system, the cold system, and whatever other storage systems we have, write a policy, and then the application builder at Facebook basically can decide how they want their data to basically perform and how they want their data to be stored. So this is a pretty flexible thing, and I'll kind of jump through just the specific cold storage side of this, which is, so main storage, it can be any of these storage systems. Keep doing that. So if there's a content that needs to be moved to cold storage, essentially this cold storage client will grab the content, it will pass it to the staging service. The staging service will essentially take this file, break it up into a group of chunks. Each chunk has a checksum, and then there are parity chunks that are added. Those are the yellow dots at the bottom here. Essentially then, from there, the streaming service works with this service that we call the storage device service, and these two work together to basically push those chunks into the raw storage nodes themselves. Some of the things that they have to manage, this is not that simple, because what we have to account for is making sure that we're only writing to devices that are active. We don't want to light up all of the spindles in one of those rooms and blow all the electrical breakers, right? So I want to make sure that as we do this, that we're managing the power capping of the servers of the data center. We want to make sure no power supplies are shared across when we store an individual chunk. And we also want to make sure no top-of-rack switch is shared across storing these different chunks. So that way, if there's any failures in the system, we can basically mitigate that by basically distributing this thing really, really wide. So the end state of this file actually looks like this. So you can see kind of it's stored on the cold storage nodes. Now, two last points here that are important. One is that when we want to reassemble this file, we'll basically pull this file off all the cold storage nodes, bring it back to the staging area, assemble this file, and then hand that file back to whatever application needs the file, right? The other thing that's important is just like, and so I don't have to answer this question 20 times later today, if a user deletes a photo, it is also deleted from this system. $1 for every time I get asked that later today. Okay, anyway, so I want to move to the next piece, the final piece, which is the actual server. And there are some examples of the actual servers floating around today, so if you want to check it out more closely, you can. But here's our cold storage rack, our rendering of our cold storage rack, and you can see the kind of the sleds there for the raw storage and the compute nodes. Some of the specifics here about the rack. So basically, it's 8x more storage capacity than our normal storage racks that we have. A minimum of 2 petabytes of actual raw storage for an individual rack here. 2 kilowatts of power per rack, which is 1/4 of our traditional storage rack. So you can see we really, really worked on density, but low power usage here. And then the standard sort of 10 gig to the host and 40 gigs out of the host. And some of the stuff that I think Frank talked to you about earlier today may change some of these specs over time as well. So again, one of the things that I should also mention here as we zoom in on an individual server is that we've actually, working with the software components that I talked about, we're going to minimize the power utilization that each server has in the system, but we also want to minimize the rotational vibration that's induced. So we're basically working on a system here with the software and the hardware, merging them together so that no one drive is spinning, or only one drive is spinning at one time in one of these trays. That's why we need to have the sophistication in the software to know which drives are active and which ones aren't, because if you spin up all 15 drives in a particular host, you may actually then overconsume power or end up causing some other electrical failure. So let's take a peek inside one of our servers and talk about the actual storage devices themselves. There's a lot of options here. We looked at a lot of things. We continue to look at a lot of different things. The two things that I'm not going to go through all the pros and cons of all of these different options today. Two I want to dive in on are the last two, so the shingled media and cold flash as well, what we're calling cold flash. So, you know, drive densities today are basically tapering off, right? The law of physics is really kind of not in our favor anymore. One of the interesting techniques that the team has discovered and is basically researching and working on now is using the shingled writing technique. The idea here is that basically when you're writing a new track, it's overwriting part of the previous track, so that only a little sliver of the actual previous track is left intact. Now this is really good if you have largely sequential writes and random reads. It doesn't work if you're shaking the disk or you have lots of sort of random I/O on the disk. But this actually fits and could fit our needs for something like photos really, really well, where basically each photo is sort of an idempotent, you know, blob of data, and you don't go change it, and you can just kind of work with that. Now the idea here, or the hope, is that there will sort of be 30% more density in this thing, and as manufacturing capacity builds up here, the cost should actually also go down. Now as another aside, one of the other interesting kind of crazy ideas out there is Blu-ray discs for big data storage. Now I think, you know, the advantage of something like Blu-ray might be that one is that there's like zero power at I/O, so really, really low power consumption. This stuff, this media has great durability as well. It will read and write sort of for a really, really, really long time. It never wears out compared to something like tape or spinning disks as well. But we'll have to keep an eye out for this. We don't have a specific need for it yet at Facebook, and we need to make sure that the costs actually come down to support something like the mega data center that we run. Okay, so I want to talk about Flash next. So I believe today that the industry today is very focused on Flash for high application or high performance application storage devices or applications. So you know, you throw Flash at applications that really need high IOPS, they like very consistently low response times. It can be really amazing. We use it, we love it. It's great for certain workloads in our environment. And I'll show you a graph here of sort of what it does and impacts. This is a real life workload on this server here in Facebook in production. This is actually a disk-based system, so the same workload is on a disk-based system. And you can see kind of in the middle of this workload how the read times spike up. So higher on this graph is worse. You can see how it spikes up here and then comes back. Now, the bottom line, which hopefully you can barely see, is actually the same workload on an all-flash design system. So not only is it way lower, but it's also very consistently flat. You don't see the erratic sort of spikes that are in the blue line here. Now, we use Flash for a lot of our key performance-driven workloads, but this performance definitely comes at a premium price. Okay, so here's the problem I see in the industry. Well, at least for us, we have hundreds of different services that our engineering team builds at Facebook, right? These services all have to support massive scale. We have 1 billion users and it's growing rapidly. We have all of these, you know, interesting products. We launched Graph Search yesterday. Things are constantly changing in our environment. Essentially, all of these engineers basically build these services, and each one of them to us in the infrastructure team looks like a snowflake. Everyone wants to be different in the team. So, you know, we have to, though, when we translate those results from the software, hey, they want to build this service like Graph Service. How do we actually support that from a hardware and a data center network and sort of core software perspective? You know, we're forced to kind of choose between two things. It's basically Flash or spinning disks. And some people try to mash them up and kind of come up with different mix-up of there. But really, fundamentally, it's spinning disks or Flash in the data center. And, you know, so here's an analogy for you that I kind of came up with, which is you go to the dealer, you ask him for, hey, I want to buy a car. And they basically present to you two options. It's either this or this. Spinning disks or Flash. And they're like, all right, cool, I'm going to walk down the street and try another dealer. Well, guess what? Next dealer, it's either this or this, right? That's it. You scour the planet. Every dealer you go to, two options. That's it. So for us, it really puts a crimp on innovation. We can't develop our products fast enough, and we really have to kind of start shoehorning things into things that are suboptimal for us. And we spend a lot of time trying to make things more efficient and being able to not slow down the product lifecycle. So what we're really looking for is something on Flash that has low write endurance. But what I want to make sure is that as we do that, that we can drive down the per unit cost, or sort of the cost per gig, right? So I want to be able to kind of, for photos, be able to get a large volume of this low write endurance Flash and be able to deploy that for some of these different tiers that we talked about. So what I really want is this. Okay, so what we actually do here is we need more choices, and I think that hard drives aren't going away anytime soon. There's this huge scale of big data that we talked about, and we're going to have to throw everything at it to keep up with it. And it really comes back to me, or it comes back to, for me, is kind of going back to first principles and making sure that we start to innovate a lot faster at the actual storage device layer. Okay. So how does our solution actually stack up? I talked about how we have this massive scale, and then we're kind of inefficient in the data center and inefficient on the servers. So how did we do? One of our main goals was to actually drive down the cost of building this infrastructure. So on the server front, we did the analysis, and our cold storage rack comes in at 1/3 the cost of our conventional storage rack. This is really cool. Now, on the data center front, our data center came in at 1/5 the cost of our conventional data center, and these are the data centers we build ourselves. So this is not bad, and I think this is our sort of V1. We're going to keep working on this and see if we can do better. Now, this whole stack optimization is something that most companies can't do or won't do. I think it's one of the main strengths at Facebook, and that as we try new approaches to solve our problems, we'll share them with the world via open compute. As we learn from these problems, I hope that we can actually help the industry move faster to solving the problems of keeping up with this big data, the big data growth that we see here. So I think, why does this all matter to you? My friends that I talk to in the Valley always tell me, hey Jay, like, you're crazy, because the stuff you're dealing with at Facebook is like 5 years in the future, right? And I used to believe that 2 years ago. I used to be like, yeah, what we're doing is kind of crazy, it's big, and it will get to mainstream, or other people will deal with this many years down the road. But I do believe that things like Hadoop and Hive and HBase and all this open source software that's coming out is really accelerating the growth of big data adoption across the board, right? So fundamentally, our big data challenges that we face today are definitely going to be your big data challenges tomorrow. I do not think that that's slowing down, and I think essentially you can't sort of push this problem out. It's sort of, back to the future, I guess, in some ways. For us is that the data here is, the data growth is unprecedented. We need to keep up kind of coming up with more advanced solutions to the storage problems here. I think the industry has been more focused on the applications that sit on top of the big data stack. They've been building all sorts of different user applications to provide more insight, to support the growth, to sort of provide more value to the enterprises here. And I think that's, really, really, All right, we'll stop there. You'll see it again. So, essentially, it's a great place, and I think that there's a lot more innovation in the app side, and I think there's also tremendous more value to get in the app side. But I also believe that the underlying storage systems and the software behind it is a big problem today. The most important innovations of all time were always the problems that people dared to solve before anybody else recognized. And for us, I think the storage kind of layer behind big data is one such problem. I think that what I presented here is our solution. It is one version of one problem of this massive landscape of problems. We'll keep working on it. We'll share what we can with you guys. But there's still lots more to figure out. And I don't think that we're going to keep up if we don't work together. Thank you.